This is gonna be the continuation of the previous video. So this is gonna be the second video of my Altium design tutorial. While I was alone, I actually did a little bit modification on this topology. So here the ground of the output connector, they are actually biased to a certain voltage, and therefore we can get bipolar output. So for example, if the input, so let's say the gate driver is outputting high, which is 15 volt, then the output, we know the bias 5 volt, then you know the difference 10 volt. So probably here I will tune the voltage a little bit higher, probably 20 or 24 volt. So then we will have somewhere like 15 or 19 volt of difference. So that is the high output. And if the gate driver is outputting low, then we will see a negative 5 on the output. So in this case, we can drive silicon carbide devices easier. So that's a little bit topology modification. And oops. Yeah, and a little bit passives are changed. For example, I did a calculation on if we are outputting 24 volt on this net, then we are looking for quite some high current and high inductance requirement on this inductor. So I used to think I can get around with it using a 0805 inductor, but later turns out it's really too small. So I later chose another inductor which is 4 millimeter by 4 millimeter. That's the smallest one that still guarantees the operation of the converters always in CCM. And then since we have higher voltage, a little bit higher current, so I decided to use a larger package for the diode, which is the 0603 package, or some people call them I think that some people call them SOD 1608 package. And well, the reason I'm using this particular type of inductor and this particular type of diode is just because I have them in stock. And the reason I'm using a UFL connector rather than the more readily available SMA connectors for the same reason, just because I have a lot of them in stock. I mean, reels and reels of them. So that being said, let's start working on the PCB. And we added the diode package and the inductor package. Now let's create, let's right click, add new to project, and add a PCB that's a blank PCB that has nothing. And the first thing we're going to do is click design board options, and as I said before, I use metric. I don't want to use the snap to center, and I want to use the smallest grid size, 10 times. That's it. And by the way, I have something in the preference. In the PCB editor, I disable the snap to center. And besides that, I don't think there's any very important modifications. It's just this one is very crucial. Otherwise, when moving something, your hotspot will automatically be centered to the center of their part, or the origin point of their part. Otherwise, if you uncheck this one, you can drag and move any part of the click on any part of the part, and the part will not be snapped to center. And with that being said, let's check the rules. Click design rules. So in the top folder, we have an overview of all of the possible rules. I don't use all of them. I only use clearance and the polygon connect style, routing vias, and short circuit, solder max expansion, and the two of them. That's it. So the clearance is pretty much means the minimum distance between wires and wires, or between wires and polygons, or between whatever to whatever. So that's the minimum spacing between two conductors. And then the polygon connection style pretty much means if you have a polygon pore, then you want to use thermal relief connection, or you want to use direct connection. In this case, because as I said before, I'm designing for academic purpose, I want to have the best possible performance, but I don't care about manufacturability. So in this case, I will use direct connection. But in some kind of commercial production, probably you want to use thermal relief connection so that you can avoid tombstoning because caused by, I believe, uneven heating, because one of the plane could be a large ground plane and the other one be a very thin trace. Then you will have tombstoning on some parts. And if you're using a thermal relief connection, that would be much better. But in this case, as I said before, I don't care. I'm anyway going to use a hot air station to do manual assembly. And routing via style defines your smallest and largest V as possible in your design. And short circuit pretty much means you have two things crossed together. It will generate an error. So this is pretty much like clearance, but clearance gives you the number, and short circuit gives you whether it generates an error. And the solder mask expansion, since in all of my packages, I already designed the override them and set the expansion to 0, so it doesn't really matter. I can uncheck it or check it, doesn't make any difference actually. And as the name suggested, unrouted net. When you finish all of your routing, then you can do the design rule check, or DRC. When doing the DRC, any of the unrouted nets will be reported as error if you check this thing. And then width is the minimum and maximum width of any of your UR tracks. It doesn't affect any of the other primitives. Like if you have a fill or you have a polygon pore or whatever, it doesn't affect any of them. It only affects your line and track. Apply and clearance, in this case, I'm using 6 mil or 0.15 millimeter. And the width, minimum 0.15, prefer 0.15, maximum 0.5. Because anything wider than 0.5, I will just use fills or polygon pores. I don't want to draw very thick traces. That's also it is just a design decision, or I'm used to do that. It doesn't have to be like this all the time. And then the via diameter, the minimum in my process is 0.5, and I prefer 0.5, maximum 0.8. Via hole size, since I need to have at least 0.1 millimeter annular ring, so the hole size is going to be 0.3, 0.3, 0.5, oops, 0.5. Okay. Solder mask expansion is already over. Well, actually, I already overrided all of them in my packages, so it doesn't really matter. But I'll just set to 0 just in case I forgot something. And polygon connection style, as I said before, I use direct connect. So that's all of the rules. Right click, save, HV gate driver, save project. Okay, now we go to the schematic, design, update PCB document, and we do a validate changes, show only errors. There's no errors, that means it's perfect, it's okay. Then we can execute changes, close. Now here we know the right thing is called a room. So what is room is pretty much a region, and if you want to place your parts, so all of the parts, they are associated with the room, and if you move the room, you will see the parts move accordingly. If you move a part out of the room, you will see there's a room definition violation. So all parts must be within their associated rooms. That's one of the Altium rule. It doesn't have to be like that. The concept room is actually designed if you have a multiple channel design, or if you have a multiple sub-circuit design. In that case, you probably want to have each of the function blocks in a separate room, so that when you are doing the layout and routing, it will be much easier to do that, and you can duplicate the routing placement in each identical rooms. In this case, we only have one room, so it doesn't really matter. We can just delete the room definition. And okay, that's not a good idea if you're doing very large design, because it's relatively small design, so I can just delete the room. But if you're doing a design with 1,000 parts and let's say 10-inch by 10-inch large board, then probably you want to carefully separate the rooms. And then we introduce the thing we said before. So remember I said I name all the parts. So the second one, so the second letter of all the parts name, they be the same letter for the same function block, right? I said before that the reason I'm doing that is because I want to search all of parts that has its second letter to be exact letter, so that I can select all of them and put them aside and route them separately, and then combine them together to have an entire PCB design. So let's go to the design. Using the second search box, we can use wildcard. So a question mark means any single letter, and I means our second letter is I, and asterisk, which pretty much means any one or more letters. So this wildcard pretty much matches everything that the second letter is I. Hit enter. Now we can see all of the parts with their second letter to be I. We can select all of them. Do not use Control A. Control A will select not only them but also the other parts. You have to use your mouse to select all of them and move them aside. And now we can do the same thing for the receiver part. Select them, move them aside, and the power part, select them, move them aside. So now we see some little bug in our design. There is a chip I forgot to rename it. See here, I forgot to rename it. UP2. Now I can simply update this and then click execute changes, then the PCB design will be automatically updated. And if you have some quite major changes, you want to do this because it automates the entire process. In this case, I only have to modify one part, so I will just manually do that. So there's no parts left. That means that's all of the parts. We can move them closer, so it makes our life easier to find the parts. So we know that this is a function block, and they should be placed close to each other. So see that's why we have the concept of design rooms. So these could be 3 different rooms, and you can lay out them separately and put the rooms together. Then you have an entire board. In this case, I use different nomenclature. It's the same nomenclature for different second letters, and that is pretty much another implementation of room, but it's different than the official implementation, but I feel this one is more efficient. Of course, if you have a very large design, you want to have a lot of layers of hierarchy, so probably you want to use the different names, you want to use different schematic sheets, you want to use different rooms, you want to use a lot of hierarchies if you really have a large design. In this case, only a small design, I don't care. And now, let's introduce another bug of Altium Designer. We are importing parts from your schematic into your PCB design. I didn't see this bug in previous versions. I only see this bug in 16.05. So probably it's introduced new bug. These probably are not aligned. See that? We have a couple pixels error in the alignment. So the parts may not be perfectly aligned to a grid. See that? A couple pixels if you're watching in HD. So you want to manually align all of them. So you can choose the parts, Control Shift and D. That aligns all the parts to the nearest grid. Now you see they're perfectly aligned. And we can do the same thing, Control Shift D and Control Shift D. You'll see there will be a progress bar, so that tells you if the operation was completed or not. Okay, now let's check all the parts are aligned to grid. Yeah, see that defined grid. That's good. And let's assign all of the thermal pads to ground. Yeah, we have another thermal pad. So, I strongly recommend you to have another. You have a separate monitor. In this case, I will move this to another monitor which is not being recorded. So now I know that my left screen is the actual working area of the PCB and my right screen is the schematic. I strongly recommend you to get another screen to do this. I mean, Altium Designer, the single license costs somewhere like $8,000. So since you already pay so much for a software, so why not pay maybe $100 or $200 more for another screen? That's very useful. So let's start with the driver. You can drag a part and hit spacebar to rotate 90 degrees. See that? 90 degrees counterclockwise. See that? When you are moving or something, or you're just looking at the board, you will see this kind of very thin single pixel wires. That's called a flat wire. That tells you the logical connection between pads. These are not actually routed wires. When you routed this thing, the corresponding wire will disappear. And also, some people prefer to have the part name to be displayed on the silk screen layer. And for me, since I want to have as high density as possible, so I don't have any of the silk screens. I will just hide all of them. See that the wires, the flat wires, they will guide you, so you can pretty much at least you know that where things goes. That's very important. Without that, probably you won't know the logic relations between the pads. So the flat wire pretty much tells you these are connected. So this is the placement stage. Of course, we're going to fine-tune this thing. So the goal of my placement is to have the minimum distance between the wires, because after all we have to route this thing, and we're doing the routing work. When we're doing the actual routing work, the simpler the design, the easier the design, and also if we just try to design everything very close to each other, then the parasitic inductance and capacitance will be minimized, which means we have higher, potentially higher performance. So in this case, I want to have the best performance possible. So that's why I am trying to put everything together. And of course, there are some other design decisions, such as I want this transmitter diode to be centered. So there are a lot of different design constraints. So you have to keep in mind that you have to satisfy all of them. Okay, now let's do some. See that this one is still not aligned because this part is designed using imperial unit system, and this board, the grid is actually a metric grid system. So we can only say the center point, which is the middle of this point, or probably middle of the pin 1, whatever. The center point of the part is aligned to the grid. So the 6 ones probably are not. That is something we have to live with. Move that 10 grids. That's perfect center to center alignment. So that is the transmitter part done. Then let's work on the receiver part. Go away power part. Let's first focus on the receiver part. And so because I know there will be isolation slot between them that handles 10 kilovolt, I am going to, since the module is potted, so I don't have to care about the air breaking down distance, but still I think I should give it enough respect. I'll give somewhere like 2.5 centimeter or so. Anyway, we can adjust the distance later. The most important thing is to first get this thing laid out. So the bias resistor goes down here. So also we have a concept of signal and power flow. So in this case, the left side is the power and signal connector, and then the buffer, and then the signal consumer, which is the IR transmitter. Then the light got transmitted through a light pipe and goes to receiver diode, and then its data sink is gonna be the comparator, which is here. So that we know the signal flows from left to right. And since we have a comparator, we have to have wait a minute. The decoupling capacitor for the diode, and we have the comparator, which is the data sink, and then we have the coupling capacitors for the comparator and the reference decoupling capacitor 02 and 03. Oops. So there are actually a lot of fine-tuning of the design process because we want the best design. There are actually a lot of signal integrity and noise immune and electromagnetics things happened. So when we are doing the design, there are a lot of this kind of considerations. I'm not going to go any deeper inside these things. That's the reason you want to go through 4 years college education rather than just watch some online videos or just read some books. There are a lot of design decisions that can only be completely described or explained by having formal education. For example, why I'm not putting the this thing to the shortest path to the shortest path, because in this case probably it will be better, but it won't be too much better because anyway the majority of the noise coming from the source, and that means if I have the source introduced here and then split it to here, then it doesn't make any difference compared to put the capacitor here. While putting a capacitor here, it's not a bad idea, but I just want to align everything together. And also for the power pin, the same thing. And also keep in mind that the pin 6 is not the true ground, it's only a signal ground. The true chip ground is actually pin 2, and technically you can do that, but that will make the routing and spacing, we are pretty much wasting PCB space by doing that. And the same thing for the 15 volt. Despite we need some kind of decoupling, decoupling of the photodiode, but keep in mind that the photodiode signal actually goes into the comparator. So the ground of the decoupling doesn't have to be very close to the actual theoretical ground. It has to be closer to the actual to the ground of the comparator. So putting this here is not as good as putting it here. That is the decoupling capacitor for the photodiode. There are a lot of different design decisions. And then we have a fail-safe resistor, just in case if the comparator or the 5 volt power supply failed, we are not driving the output gate driver for no reason. And then the signal goes into the actual gate driver. And of course, when we have a chip, we know that we have to do the decoupling, which is CR4 and 5. I prefer use a large one and a small one so that they handle, each of them handle different frequency. The larger capacitor provides bulk energy, and then the smaller capacitor provides high frequency response. We know the actual power pin is going to be pin 5, so I will put it as close to pin 5 as possible. And also always remember that the smaller capacitors goes closer to the chip. The large capacitor goes further away. Pin 1 and pin 8 are just enable signal, they're not the actual power signal, so it doesn't really matter here. You know what? I'm going to put it here. And then put a ground via here, so we have a minimum ground loop. And the placement of this capacitor doesn't really matter anymore. So probably I'll just place it somewhere random, it doesn't really matter anymore. Anyway. And then we have the output resistor and diode network. The bias is going to be CR6 and CR7. I'll move them around. and we know these are the outputs. Keep in mind that the UFO connector is a very low profile connector, so make sure if you want your cable goes out this side, then keep in mind that you shouldn't have any large components on the right side of your board. So these things go here. Oops, that's the wrong package. And let's add some smaller capacitors to decouple the 5-volt path. So we copy these parts, and if we just paste them, we will see that we don't have any net information on the paths. So we have to use edit, paste special, keep net name. So we paste another set of them. We set a smaller package. Bingo. So that's pretty much a receiver layout. Let's align the parts. Let's have more spacing between them because they are actually connectors. We have to make sure that we can connect cables. Okay. I'll leave a little bit more. We'll leave just 1 millimeter distance. I will leave a little bit distance here because I'm going to place a via here so that we can bring the power into this thing. Let's try place a via, let's see if it works. It just barely fits the space. Okay, that's good. And by the way, if you place all the parts aligned over, pretty much they're aligned to each other on the same horizontal or vertical space, then we are doing the actual pick and place, we're doing the actual assembly, it will make our life much easier. So be nice to yourself. I want to align them together, so I think that's 2 coarse grade. Still work. I think that will be it. I can always align them. Okay. So now we are left to the last part, which is the power part. I want the power part to be here. And this time I want the battery to be connected from the right side. So, oops. I forgot the ground symbol in the schematic, so I have to copy and paste. So in this case, if I am going to replace the net symbol on all of the parts, that would be very tedious. So I will use, so I forgot, you cannot see the other screen, so I forgot the ground symbol here. So all of the parts, this should be ground, but all of the parts are now net whatever, net CP1-1. So that's, oops. So now we have to update the design to fix this bug. Execute. Okay. Now we move back, we remove the room definition, and now we have ground. Thanks. There are some minor bugs here, I don't know what happened. Oh, that's supposed to be 0402, okay. Okay, in the schematic we'll just fix this one. That's CR4. Go away. So now we start from the battery. As I said before, I want to have some distance. I'll just align them to this grid. Let's see the distance. So by the way, that also defines the size of the board. Now here the distance is 1 centimeter. So since it is 10 kilovolt, I would say yep, even it's potted, I still want to have enough clearance just to make sure nothing very horrible happens. Now since we know the distance of the design, the size of the design, that is 50.5, let's make it 49.5. So now we know the size of the design is gonna be 49.5 by 15.5. Now we can draw the outline of the board. You go to mechanical one, or you can use keep out layer, it doesn't matter. That depends on how do you want to export a Gerber file, but after all, this should be the same thing. I prefer to use mechanical one. Place line, oops, PL. And there will be a clearance. In this case, well, the distance between your design and actually the board edge, it all depends on your PCB manufacturer specification. So before you do any of the design, make sure your fab can make that for you. The reason I moved the left part 1 millimeter below is because I want to cover the left part with the ground plane. The reason I didn't touch red part is because this is the only ground, and anything after that, it doesn't have to be in this current loop. So it doesn't have to be perfectly grounded. So whenever you're designing your placing or layouting a board, always assume that if you are the electron itself, where do you want to flow in your typical expected current or using case. So in this case, if I know that's gate driver, we know that we dump a signal, we dump a current from this capacitor, goes through this device, and then goes through the resistors, and then directly go to the device being driven, and go back. So you know that's gonna be the current loop. So you know the largest spike in your current loop is gonna be the ground loop is gonna be from this point back to this point. So you know that is where you should really worry about the minimum inductance. I think I forgot this pretty special. It's all about art and science. So see that if we're driving a signal, so we know that the charge in this capacitor goes through this device to the resistors, through the resistor to the output, and flows back to the return point, and the bias capacitor, and then goes back. So that's a very tight loop, and that guarantees the best performance. Actually, if you want to further squeeze out some better performance, you can do this and move all the parts closer. That's also a very good idea, but in this case that will reduce the effective size of the ground, so make your choice. I'm not going to do that. Let's see how to do the power layout. Let me see. I can start from 5 volt, I think, or whatever. I will start from high voltage. So the high voltage part is gonna be, of course, before everything we need a fuse. And the input decoupling, CP1, CP2. Here we only place CP1 because CP2 is gonna be reserved for the other converter. Then we know we have the large inductor. And the controller. And now we have, where's the output? Here's the output. Okay. Here's the switching node. We know that. And keep in mind that here we need a very consistent ground path. So I'll try to leave at least a millimeter of ground plane here. And then we have the feedback. We have RP2, CP3, RP1, RP2, CP3. Yep. And of course output capacitors, CP4, 5. Since here is the power user and here's just the power source, we'll just place the capacitors in this way. Okay. There is the high voltage. Okay, there's the high voltage. Okay, I think that's all of it. Now let's move on to the charge pump controller. CPU2 is always the other decoupling. Then we have the actual device. Oh, I think, yeah. I have to set the ground once again after I did the schematic update. The flag capacitors are the one CP8 and 6 and 7. They are the output. The flag cap is and where's the output? It looks weird because we want to try our best to avoid this kind of cross. The reason I'm doing this is because we cannot, even if we can place it very closer, even if we do that, we have to create a via to connect pin 2 and pin 6. So anyway, we need some extra space. So I will just align all of the grounds pointing down. And then finally the bias generator. Let's find a place for this thing. Move the large capacitor away. Because after this point there's no any ground, so I don't have to care about the ground plane consistency here. I think looks okay. Now we fine tune the size. For God's sake, I forgot another label. For God's sake. I don't want to do that once again. I will just manually edit all of them. Oh, by the way, if you want to highlight one of the any net, you can hold Control and click on the pad. Then all of the nets of the same, all of the pads of the same net will be highlighted, including any of their traces, polygon pores, whatever things. Don't have much space here. Let's see how can I maneuver the space. Still enough. That's not looking good. I'll just remove this capacitor, it doesn't really matter. Just remove it. The clearance cannot be satisfied. I have to move this away as well, seems like. Okay, now I think we should have more than enough space. Let's just move it here. You know what? These are not aligned, and that drives my OCD crazy. I don't like it. I really don't like it. It really drives me nuts. Thank you. That looks better. Anyway, so that is pretty much the final layout. Then we have the ground plane separation between them. That's gonna be 19. I think 15 is gonna be more than enough in a potted environment. So I will call it a go and start routing process. This router spent a lot of time doing the placement, and we know the placement is almost perfect because we know we pretty much have all of the affiliated parts together, so the routing should be rather easy. To place a track, place P, and keep in mind before that we were drawing the mechanical lines and drawing the silk screens, we used PL. Right? And now if we're going to draw actual conductor traces, we can also do PL, but later versions of Designer will not assign nets for these wires, and then we will get a DRC violation. If you consult Altium's feature document, they said that kind of drawing mode has been deprecated. So now you're going to use interactive routing tool, which is PT. So we click P and T. Oops. P and T. Yeah. Then we click the starting point. It doesn't have to be the center. It will be automatically snapped to the center. It doesn't really matter where it started. See that? I click here and it was automatically snapped to the center. And then you can click the destination. Double click, right click to finish the line. Also keep in mind when we are doing the drawing, click and then you can see the line. You can hit tab key and you can set the line width, all of the parameters, and you can set the VS size if you want the interactive router automatically shift layers for you. But in this case, I always plan the VS myself, so I don't need this feature. It doesn't really matter. So this case, the power trace, I will use 0.3, left, left, right, and then we have left, right, no, left, and we click whatever part of this path, it doesn't really matter. In the left, left, right, now we completed this layout. Then left, center, left, left, right, and left, left, right. Oops, we have to have the space to connect them together, so we need to place a via. Place via 0.5, 0.3. So seems like we cannot use 0.3 tracks. Control C and Control V. Now we have the vias. So now we are going to use thinner tracks. I will say 0.15. Click here. 0.15. Okay. You see that when we are moving this thing and it moves closer to the via, as it moves closer, it probably will reach the point where it breaks the rule. And then Altium Designer, the interactive router, will not allow it to move any further. So that is the algorithm you are paying so much money for this tool. It's very automated, very smart, despite sometimes it can do some really stupid things. Okay, we are finished with this. Then we route. One, two, three, so now we're done with the majority of the part. Let's add some vias to the power decoupling path. It's too much. Let's add some more if we want. Performance is critical. Aesthetics is as critical as performance. I think that's it. Now we can finish the ground connection. Oh, I forgot the connection between here. Because of the complexity of the right part, so I believe I need to use a 4-layer board process. So to have a 4-layer board, you click design and manage layer sets. Oops, no, the board layers and colors. No. Oops, where it is? Where it is? I forgot that one. Oh yeah, layer stack manager. You simply click add layer, and then add layer, then you will see a signal 1, signal 2, and top and bottom. Click OK. Now we are going to route this on signal 2. And that's another topic, that how do you design which layer is ground, which layer is signal. Generally for four layer PCB, people prefer to use the top layer and bottom layer as routing layer, and then mid 1 as power and mid 2 as ground. However, I prefer to use top and top layer as the most heavy routing layer, and mid 1 and mid 2 as another routing layer, and mid 2 and mid 1 and bottom, I prefer these two layers as grounding layers. There is a lot of discussions about this topic, so I'm not going into this thing. So I just do this with my way. Now finally we have the ground plane. We click place and polygon pour. Top ground. Let's first pour on top layer. Connect to what is the net for the input side ground. CI1-1. Top ground. CI1-1. Solid region. And if you want to remove some smaller island or remove some necks, go ahead. Pour over all same net objects. Top layer. Okay. Once again, the clearance between the four sides, they are all up to you. So if you have another layer of insulation, for example, I'm going to use a plastic housing around this thing, then you can approach the margin. But if you want the PCB itself to be the insulation material, then you will have a donut around the design, and that serves the isolation purpose. Oops, I forgot this trace. Oops. I forgot this one. By the way, if you hit your shift and space, you see you have different routing styles. Circular, right angle, circular arc, and any angle, and 135-degree angle. Okay. PG top same thing. Click. And because I don't want to click all the points, so I will go to the right angle mode, just because lazy. Okay, that is the input side. Let's move on to the output side. Let's start from this signal. You probably want to know why I don't just connect them together. is because I want the signal first go to the termination resistor, then go to the comparator to remove any possible glitches. You probably will never see the real benefit, but if it really happens, you could screw up your day. So just be a little bit careful. Extra careful is always not a bad thing. Okay, now you have to have, let's consider grounding issues later. Okay. Just because it's a power signal, deserves some extra length. So the same thing here. Let's go wider. Okay, because we know the signal comes from here, so we add a via. There will be a lot of ground vias later. I will add them later. So first is the signal and power, and then ground. And seems like I don't need this via anymore. I can add a via here. Okay. The same reason we add here is not rather than adding here is because here we're going to generate a lot of switching noise. I want the noise to be shunted to ground using these capacitors, then goes into the power source. Otherwise, the trace between here and the power source will irradiate EMI interference. So for the sake of EMI compatibility, I want to add the via before, after the cap. not between the cap and actual switching node. But frankly speaking, it should not make too much difference at all because these are really not high current traces. This is the real high current trace. See that? I should have placed it over here, but I don't have the routing space. So I have to compromise here. And by the way, you probably want to ask why I'm using the 135-degree angle rather than just right angle. Well, that's because this kind of angle has less EMI radiation, and also it has better signal quality. At a couple of tens of megahertz or even lower frequency, it's pretty much just a myth. You don't really see any real benefits. But after you go up to a very high frequency, you will see a difference. And for this kind of low frequency board, it is just a good legacy. And also for some PCB fabrication process, there will be some phenomenon called acid trap. And this kind of corner design can mitigate that problem. It's not something you have to do it that way, but it's never a bad thing to be extra careful when you are designing something. Lots and lots and lots of vias, ground vias. Probably doesn't make too much difference, but look better is not a bad thing. I will add a field here. The reason I'm filling up this space is because this is a connector, and it will see a lot of stress, mechanical stress. So to prevent the part or the PCB trace beneath the part to be lifted off board, we need to have a larger surface area so that the stress on this pad will not just peel off the entire footprint. So if you have just a small pad, you probably need 1 Newton or 2 Newtons of force to peel off the pad, especially at higher temperature. It will be very fragile. And if you have a larger pad, then peeling off the entire copper will be very hard. So that makes the reliability of the connector much better. Small design tricks. I think the signal part is finished. Let's add some thermal vias. Yep, that's it. Then we have tons of ground vias. Just to reduce the parasitic inductance. Save. The reason I'm doing that is because I want to have some ground shielding here, so that the 10 kV common mode noise coupled from left side to right side will not end up in my photodiode. So we also need some ground pads here, guard pads. That's called guard pads. So I think that's it. I will fine tune the size later. Okay, let's go on with the power part. Okay. Okay, we place something here. That's gonna be input decoupling, and that goes all the way here. Press P and F to place a fill. So first we need to know where do we need vias. so we have to plan the space accordingly. No, I'm not doing that. Oops. Okay, so what we did is I want to increase the size of this thing so that we have lower resistance loss. So that's a concept I was always thinking that while doing the actual layout in every step of the process, we have to think optimization. We have to plan for the next step. That's the key to a successful design. So where things can be optimized and where can we reduce a little bit loss, and where can we reduce a little bit EMI interference. Always plan them. Now we finished this net. As we said before, the ground will be left there. I will use a polygon port to solve the ground issue later. So essentially what we're doing when we are planning the grounding is we want to minimize the, since we have the ground planes, we want to minimize the cut of the ground plane as much as possible. So we finished the 5-volt net. Now we have, here we have another net. Let's see how to do that without cutting too much ground plane. Okay. Now let's finish it off. Oops, what happened? So in the real world board, it could be much more complicated. In this case, it's so easy because this is a very simple board, and technically, if I want to squeeze this, if I just want to do more manipulation, I can do this with only 2-layer board. Anyway, for a signal integrity purpose, anyway, I'm going to use 4-layer board. So in this case, this is the kind of anyway thing. But if you are designing something that's really high density, or you're looking for the absolute minimum cost, then in that case, probably you want to think twice before you do all of this kind of waste of board space kind of thing. So if that's the case, you probably have to spend much more effort to try to squeeze things together, to try to optimize the wires, to try to stitch the vias. A lot of things happen, and that's the cost you have to pay if you just want to have the cheapest possible board. In this case, I don't care about the cost, so that makes my life much easier. Anyway, 4-layer board is our standard process. Okay, now we are going to pour the ground. Let's see all the nets except, oh, forgot one. And I believe now, yeah, we have another one. Now it's only ground left. Okay, let's do the business. Pour ground, top ground, ground. So now I can see the ground has been poured. And then we can tune the size of the vias. Okay, see that the ground actually protects these trees. So that's kind of shielding effect. Now it seems like we need more vias here. Oh, I will just move it here. It doesn't really matter. I think it's okay. Now we can start moving on the next layer. PG and one ground. The name doesn't matter. Just because I want to give it a good name, it doesn't really mean it has to be the perfect name. I mean, this time I name it M1 ground. I can name it whatever thing I want. And then let's place M2 ground. And finally the bottom ground. The reason I'm using M1 layer as ground and top layer and signal 2 layer as routing is because M1 ground will shield any kind of cross interference between traces on top layer and traces on M2 layer. And I prefer the ground, the bottom layer to be ground is because sometimes I will just place the board down to a metal surface or down to a case, and I don't want anything to be interfering the board or the board splitting EMI radiation interfering anything else. So I prefer the bottom layer to be a solid layer of ground. So EMI things and RFI things will be made much easier. Let's add some via stitching. So let's stitch the ground. Oops, that will not work. Okay. Okay. Oh, there is a field. Okay. Oops. I think now we don't have any ground islands. Just in case, let's add some more. Now I don't think we have any ground islands here, so that will be the design. And now let's focus on this part of the design. I don't even think I need too much ground staging because the main current path is so small. Okay, let's add more layers and one ground, C11. And finally bottom. And now we have the entire design done. Then Let's see what we're going to do next. You can select multiple objects using pressing Shift key. Some fine touch. Top layer M1, M2, ground. There's no island. Good. So finally, we're going to define. Oh, by the way, I'm going to cut the size to 0. Now that defines a precise line of your of the parameter for design. Finally, we create the shape, the board shape. Press 1 to go to board planning mode. Press D to go to design menu, and redefine board shape, or just short key 1DR. And as usual, we draw the side of the board. Click, left click, right click, and we press 2 to go to the 2D design mode, or 3 to go to 3D render mode. Altium can go to 1, which is design mode, plan mode, and 2 is the 2D design mode, and 3 is the 3D design mode. Okay. Now we can add some logo if we want. So go to top overlay, which is screen layer. Then let's add. I don't like the screen layer. I prefer to use the solder layer, which is the solder mask opening layer. We can place a string or PS. Place a string here. Copyright my name. Let's make it, how to do that, multi-line. Yeah, multi-line. The height is, let's say 2 millimeter. That's too large. Yep, that's perfect. Our lab, university. It looks nice. Now we have 1 millimeter border. That looks not bad, or maybe 1.5. Yeah, that looks not bad. And let's add some notice. Warning, high voltage. Roughly the center is 1.75 is gonna be 0.875. Okay. Let's see the distance. Now it's perfectly centered, I believe. 1.625. 1.625, perfectly centered. Which one looks better? 4, 5. Oh, so this one looks better. This one looks a little bit better. Okay. So we finally finished the board. Now we can export the board into a format that can be manufactured. Save the board. And by the way, we have to do a DRC just to make sure we don't screw up anything. Tools design rule check, run DRC. There's no error. That means it's okay to go. Now we add a new file, which is the output job, and we want to output the Gerber file. So for folder structure, I will use manually managed. Just say output. Okay. There's no any folder. Advanced. These are just my preference. It all depends on what you need. Fabrication output, we add Gerber files, we add NC drill files, and we click the folder structure, then we click on the radio buttons to enable them. Gerber I use 2 to 4. I want to plot these layers. Now we are using mechanical 1 as the board shape layer. If you're using keep-out layer, then you have to plot this layer instead of this one. So that depends on which layer you drew the outline, which is the green line. If you're using keep-out layer, it's gonna be pink. And I want to keep the leading and trailing 0. That depends on your PCB fab's requirement. In this case, I want to use the OSH Park service, and they want me to keep the leading and trailing zeros and use inches 2 to 4. So I'm just following their requirement. Save HV get driver. I also want to generate the PCB document. I mean the schematic and the PCB 3D view and assembly guide. So I want to generate PDF files. Double click, manually output, and advanced. I don't want to add them to my project. I don't want to include all of the information, just bare minimum PDF. Okay, and then we can add document output, schematic. That's the first one. Then we add a PCB 3D. I think it's PCB 3D print. Yes, PDF 3D requires some new version of Acrobat to open. It's a completely different thing. Okay, then we click. This is the first page, second page, and then we add assembly guide, assembly drawing. Okay, this is the third one. And double click for the options. I only care about top layer, so I can remove these other layers. Anyway, there won't be parts in the middle layers. So I'm not sure why Altium defaultly generates the middle layers. I think it's stupid. Nothing more preference, okay. And PTB3D print. For a better resolution, you can have 300 dpi, but I discovered in 300 dpi there are some bugs. Sometimes you will see a split lines for no reason, so I use 150 dpi. As I said before, Altium has quite some bugs. I don't want all of the marks, I just want the bare minimum schematic. Now we can save the outdrop file, and then if we want to generate a PDF, we click the PDF and click the generate button. Okay, it's done. And then we can click the folder structure and then also click the generate button. It's a different icon but still generate files. Okay. Now we can go to the actual folder. We have generated output folder, and then we have the PDF, which is okay, but where is my assembly files? Oh, it's here. So why it's not in my intended folder? Let's see. Oh, it should be output. That's also a bug. So when you first edit any of the preference here, and then you add some other documents, then this folder name will be overwritten. That's a bug. Okay, save, generate. Now we should have, yeah, we have the PDF previously generated, and we have all of the design files. So I hope you enjoy it. That is a completely flow of designing a very simple board using Altium Designer. I probably will later cover some other topics, but I'm not really sure about that. At least right now we have a very basic tutorial of how to use Altium Designer. So that's it.